So hi everyone, my name is Andrew. I'm currently working as a postdoc at Newcastle University in the UK, but today I'll be talking about some results that I got while working as a PhD student at Monash University, which is in Melbourne, Australia. So I was studying 2D quantum turbulence in boson-snake condensate systems, and in particular, as we'll see, I was looking at the formation of large-scale flows in these systems. So my talk today will be broadly split into two sections. So in the first part, I'll kind of introduce the problem and talk about some theory work that I did. So I'm a computational physicist myself, and do a bit of theory as well. But in the second part, I'll also talk about an experiment that was done at Monash. And even though I'm not an experimental physicist myself, I got to collaborate with the people in the lab there, and we got some really interesting results out of that. So before I dive into my own work, I'll just talk a little bit about the background of 2D quantum turbulence, what it is, and why it's interesting at all. So intuitively, it's probably kind of, it's probably most intuitive, to introduce quantum turbulence by comparing it to classical turbulence. So in 2 dimensions, classical turbulence might look something like this. So here we just have this complicated swirling motion of some fluid. And so here, the kind of black and white blobs you see are vortices. So that's where the fluid's either swirling clockwise or anti-clockwise quite strongly. But the vortices that make up this turbulence are kind of continuous in the sense that they can be any size or shape and any circulation strength. So they're kind of complicated objects, and they're not really well defined. So it's pretty clear that something like this, or this is a vortex, but it's not really clear about whether this or this is a vortex. So they're pretty complicated. By contrast, quantum turbulence in 2 dimensions looks something like this. So this is just an image from one of my simulations. So this is just the density of some boson-snake condensate, and the black dots you see here are quantized vortices. So that's where the density goes to 0. So at the moment, the 2 pictures look pretty different. But around each of these vortices, there is flow circulating either clockwise or anti-clockwise. And when you sum up all the flow fields from all these vortices, you'll get some streamline field that looks something like this. So qualitatively, the actual flow fields do look quite similar between these 2 systems. And so there's actually quite an interesting kind of a comparison. And a lot of interesting physics is shared between the 2. Yes? Sorry.
How do you deal with boundary conditions in this case?
So I'll get to, well, you'll see this right now. So in my PhD, I was looking at a disc-shaped trap. So I have a cold gas that's trapped in a circular boundary. So here, the grayscale in the background is the density of the fluid. And again, you can see the black dots of vortices. But I've also indicated here which vortices are clockwise or anti-clockwise with colored dots here. So the blue ones are vortices and the green ones are anti-vortices. And so just to give you an idea of what the quantum turbulence actually looks like dynamically, I'll just play the simulation. So if I hit play, you just see that the vortices just start moving around chaotically and get this really interesting, crazy motion. But I guess the takeaway from this is really that most of the interesting dynamics are in the vortices. So the background fluid itself is just kind of a background noisy field. And the dynamics of that aren't really that interesting, but it's really the vortices that we're interested in here.
Red is the dipole vector.
Sorry?
Red is the dipole vector.
Yeah, so the red is the dipole vector. That's not really particularly important here. Sorry.
Do they spin in the same direction, all of you?
The vortices?
Yeah.
So in what sense? Like the blue ones?
I mean, the clockwise or counterclockwise.
So the blue ones are clockwise, and the green ones are anti-clockwise. Yeah. So there's overall a neutral vortex system, so equal numbers of each side.
So in the quantum system, there's an absolutely conserved quantum number, the number of vortices minus anti-vortices.
Yeah, exactly. So it's whatever you put in, that should more or less stay the same.
Did you have any dissipation there? It looked like there was.
No, so no dissipation in this.
So it's just
conservative, but you effectively get dissipation from the vortices into the background sound field. So you actually see the vortex numbers going down. So you get annihilation events, which basically give energy into the fluid from the vortices. So that's an effective dissipation, I guess.
So
yes.
So when the number is not precisely equal, it's because of sort of loss at the edges, or
yeah, more or less. So I'm also not counting all the way out to the boundary. So there are some that you can see I'm counting, and then you can get loss. You can get single vortices lost to the boundary as well.
What's the initial condition?
So this is the initial condition. It's literally I start with a flat pancake, Bose-Einstein condensate, and then I imprint these vortices by hand. So this is kind of an artificial initial condition, but as we'll see, you can kind of do a similar initial condition in experiments. Any more questions? Okay. So why 2D in particular? Why is this system interesting? Well, it's kind of known, again, using this classical quantum comparison, that large-scale structures are known to form in 2D classical turbulence. So a typical example is the atmosphere in Jupiter. You see this giant, the great red spot in Jupiter is this giant vortex structure. And it's thought that that has kind of emerged over time because the atmosphere in Jupiter is approximately two-dimensional, in the sense that all the vortex dynamics are contained in kind of the plane that's parallel to the surface, if that makes sense. So the vortices here are all kind of rigid, more or less, and point radially outwards. So it's approximately two-dimensional in that sense. But as with most things in turbulence, this process isn't really that well understood. So we know that this large-scale vortex formation, we don't really get exactly why it's happening. So here what we want to do is look at the equivalent process in 2D quantum turbulence and see what we can learn basically from studying this problem. So if I keep playing that simulation that I was showing you earlier, you might have already noticed that the vortices that I put in randomly at the start end up clustering into these two same sign groups of vortices. So these are kind of the quantum equivalent of one big vortex in the classical fluid. So it's when all the quantum vortices clump together. All the quantum vortices of one sign clump together. And so you can imagine the flow field around this is going to be quite large. So it's kind of system scale flow field. So this is what I was kind of studying all throughout my PhD, was this process of this vortex clustering, trying to understand it and characterize it.
So there are long-range interactions between the vortices?
Yes, so the velocity field of each vortex drops as 1 over r. So yeah, that's what drives this, basically, this, the dynamics here. They push each other around. So moving on to some results. So I'll tell you about...
Well, isn't it attracting the sign of the interaction have a effect on the top?
Sorry?
Well, you've got like vortices clumped together, right? So that would indicate there's some sort of attractive interaction.
Not... okay, I can get to this in a
That's
bit.
just a fluctuation.
No. So it's... How do I explain this? So they don't attract per se, so you always have motion perpendicular. So basically two same sign vortices will rotate around each other, and two opposite sign vortices will travel in a straight line. So you don't actually ever get attraction or repulsion unless you add dissipation into the system. So here it's conservative, more or less. So you don't see that for two isolated vortices. So this, yeah, this isn't really related to whether they travel close, whether they're attractive or repulsive, I suppose.
What I'm wondering is, why do you get clumps?
Okay, so I'll get to that in a bit. Hopefully that will be explained later. So yeah, the first part of my talk, I'll be talking about this project of vortex thermometry that we did recently. So this requires some background on negative absolute temperatures, which turn out to arise in these 2D vortex systems. So when I'm talking about temperature here in this talk, I'll just be using the usual statistical definition of temperature, which is, well, the index temperature beta is the derivative of the entropy with respect to the energy. So nothing unusual there. What is unusual here is that I'm not talking about the temperature of the actual Bose-Einstein condensate. So if you have a Bose-Einstein condensate in a lab, it's probably at something like 100 nanokelvin. So we can measure that temperature directly. But that's not what I'm talking about here. And also that temperature is always positive, I should point out, as you might expect. That's not what I'm talking about here. Here what we do is we basically treat the vortex subsystem in this fluid as if it was isolated. So we throw away the background fluid and treat the vortices as if they're kind of a gas of interacting particles. And when you do that, you can assign an entropy and an energy to the vortex gas. And because of the way we've treated it, you end up with negative temperatures arising in the system. So just to give you a kind of an intuitive idea of how that happens. If you imagine that you have, this is just a simplified example. If you imagine that you have two dice and you roll them and you add up whatever you get on your roll, you call that the energy of the configuration. Then as a function of this energy, the number that you roll, you plot the number of ways of getting each, so the multiplicity omega. So there's one way of rolling a 2, there's one way of rolling a 12, and there's lots of ways of getting everything in between, as you might expect. So we can apply this definition of temperature here. So the entropy on the numerator here is just the log of this multiplicity. So we take the log of the y-axis, we get this graph. And then you can see that on the left here, the gradient is positive. So we have a positive temperature. On the right, the gradient becomes a negative. So we actually get negative temperatures here. So what this means is that when you put energy into this system, the entropy goes down. So it gets more ordered as you're pumping energy into it. So that's kind of bizarre. Most systems don't behave that way. The reason this happens is just because the phase space here is bounded. Alternatively, the area under this curve is bounded. So Onsager showed back in the 1940s that if you have a system with this phase space being bounded, then you'll get, basically, it's a necessity that you have a maximum in this curve, and therefore you have some negative temperatures in some region of your phase diagram. So yeah, that's basically just because the number that you can roll on each dice is finite. So if you have an infinite-sided die, you could just keep rolling higher and higher numbers, and there would be more and more ways of getting each number as you keep going up in energy. But it's because there's some maximum on each die that you actually get this negative temperature behavior. So from coldest to hottest along this energy axis, these temperatures start at 0 Kelvin, go up to infinite Kelvin, as you might expect, but then they flip over to negative infinite Kelvin and come back to 0 from below. So these negative temperatures are actually hotter than cold temperatures in the sense that they have more energy. Here I'll be dealing with the inverse temperature rather than the normal temperature, just because it doesn't have this singularity in the middle. So that goes nicely from positive infinity through to negative infinity. So you might be asking what this has to do with vortices in this 2D fluid. Well, it turns out that if you have a 2D vortex configuration and you put it in any kind of container, you get these negative temperatures arising. So again, if we plot the entropy versus the energy in the vortex system, we can draw basically the same diagram as for the dice. So if you just throw vortices randomly into this container, you end up with an average energy. And so the energy here that I'm talking about is the energy in the flow field. So if you imagine adding up all the flow fields of all these vortices, and then you basically integrate mod v squared over the whole system, you end up with some energy. And it turns out that that's kind of an intermediate energy for this state. And obviously that's high entropy just because this is a highly randomized state that I've just thrown in. It's like throwing darts on a dartboard at random. It's pretty disordered. I can then, so that's the equivalent of rolling a 7 for the dice. There are lots of ways to do it, and it's kind of an average roll. To go to lower energies, we can then put the vortices into dipole pairs. So what you imagine here is that a clockwise vortex and an anti-clockwise vortex basically on top of each other are going to cancel out in the far field. So there's very little velocity in between these vortices. So there's very little energy in the flow field. You can also see this is a lower entropy state because this is now more ordered. If you're just throwing these in at random, you wouldn't get the state very often at all. So that's the equivalent of rolling a 2 for the dice. Up the other end, we can add energy into the system just by reconfiguring the vortices into these clustered states. So here, again, this is a more ordered state, and it has really high energy because now we've kind of combined all the velocity fields such that they create this big coherent flow field. So there's lots of energy in this state. And so that's the equivalent of rolling a 12 for the dice. So it's high energy and low entropy. So the negative temperatures are in this clustered region. So if we go back to this picture that I showed you earlier, the initial state that I put in, again, I put that in by hand, just in the numerics. What happens is over time, you see that you go towards this clustered state, and therefore we know that we're moving towards these negative temperatures.
So you have a measure of phase space, so that given the number of vortices and the energy, you know how much phase space is associated with that. Is that correct?
What do you mean, how much phase space? Like the entropy, I suppose?
Well, in the case of the dyes, the phase space is discrete with 12 possibilities. And, well, the defined entropy is the normal definition of entropy is probability, but it's in some phase space. You don't.
Wait, sorry.
Yeah, well, I don't see how you actually are measuring the.
How do you calculate the energy and the entropy for a given system?
So the energy is
Yeah,
straightforward.
okay, right.
Okay, there we go.
Energy is easy.
Energy is easy. That's just the mod of the velocity
Why
field
it's
squared.
easy? Because the vortex spreads would be a higher volume than
Yes.
calculate the energy of one vortex. So I don't know how you.
Yeah, okay.
The algebra is there.
So what you get out when you calculate the energy of a system like this is you basically get each vortex has its own energy term. It's like the self energy of the vortex, just by putting that in. But then you also get interaction energies between the vortices. So here, I guess the self energies are always going to be constant, I think. That just depends on where you put it in the fluid. But when you put it as dipoles, the interaction energies are going to be much smaller than compared to this case here.
So
if that makes sense.
You take the velocity field squared, multiplies the density, and integrate over the surface.
Yep.
You go all the way to the boundary.
Yeah, exactly. So in this case, it's easy because we do have a boundary. But if it was infinite, then there's basically you just
So
implement
you
a
find
cutoff.
out, for example, the left picture has less energy than the right picture.
Yep.
When you do this.
Yes.
Divided per vortex, I think.
I know. So well, if you keep the number of vortices the same, you can ignore this. So if it's a constant number of vortices and you arrange it as dipoles, you'll have much lower energy than if you arrange it
But
as.
you started with a large number of vortices, you ended up with a small number of vortices, and for that reason, you divide by the number of vortices to get this behavior.
Yes. So if you look at actually just the energy of this vortex state, you're actually moving. You're moving towards lower energies, but it's because you're moving towards lower energies slower than you're losing vortices, then you actually move upwards in this graph. If that makes
And
sense.
why is that reasonable to perceive this way?
In
Why we'll not put the total energy of the system, we'll put the energy per vortex? Because you see, you're looking at the entropy for a single object. You see, what you see for that seems like the quantity you're looking at, right?
it should be
Not the entropy of the entire system, which is the typical thing for thinking.
I think that you sent there for this argument to take into account that the Hamiltonian is the logarithm of the positions, or better to say, of the differences of positions of pairs and all of the sum of those.
Yep.
Now it's a 2D gas, so for this Hamiltonian, the coordinate is simply the coordinate in one direction, whereas the canonical conjugate is the coordinate component in the second direction. That makes up the phase space.
I see.
So essentially, you just
okay.
divide
Sorry.
up the space into bins of minimum size, which are given by the size of the core. And then you have
Okay.
Yeah.
states.
Sorry.
Okay.
Now I understand your question. Yeah. Yeah. So basically, as I was saying, it's basically because you have this vortex gas in a bounded container. That's what bounds your phase space, because it turns out that the phase space is equal to the real space in the system. So if you have an infinite system with vortices, you don't get these negative temperatures. Sorry?
I have a much parallel. Why don't the vortex and anti-vortices just annihilate?
So in the dynamics, they will do this. They will annihilate.
And on the right, there's no intrinsic, say, charge 2 or charge 3 or charge 4 vortex.
So there are, you can get multi-quantum vortices in these systems, but basically it costs energy to combine two vortices into one multi-quantum vortex. So it's, yeah, exactly. As soon as you put in,
When they decay,
sorry?
how do they decay? Because they have to give off some energy. What do they give off?
They'll give off sound waves, so you get some fluid oscillations, basically. Okay. Yes, okay. So already comparing the dynamics that I showed you earlier, we can see that we have these negative temperature states emerging from what we put in as a fairly random state. So it looks like we're moving to the right in this diagram, just intuitively.
Now, you know the spaceship, you kind of ended up at that stage, but I think you proceed, probably you'll end up with no vortices at all.
Yes, so in the end, so what actually
But
happens
the
is,
process slows down.
yeah, exactly. So what will actually happen is we move this way and then it slows down and you actually start moving back this way. And eventually all your vortices will annihilate. So at the moment we haven't run until the ultimate fate, which takes a very long time. So what we wanted to do here was actually get out a quantitative measurement of this temperature parameter, which hadn't been done before. So given some state of quantum turbulence with a lot of vortices and anti-vortices, we wanted to be able to stick in the thermometer and actually get out a quantitative measurement of what the temperature reading actually is. So to do this, we need some monotonic function of the temperature. So here, we need something that we can measure directly from the vortex gas, and then we can just line that up with the thermometer, whatever the thermometer happens to be, and read off what the temperature is from the x-axis here. So how do we actually do that? We found that the most robust way that we found, at least, to do that was to classify the vortices. So we wrote this algorithm. It was based on a similar algorithm written by some other people at Otago in New Zealand. And basically, it splits the vortex, any vortex configuration, into 3 groups. So the most important 2 are the clusters of same sign vortices and the dipole pairs. And then whatever's left over after these 2 have been identified, we call free vortices. They're kind of just on their own. So just as an example of how the algorithm works, what it spits out, if you put in some configuration of vortices and anti-vortices, it will spit out, it will tell you basically where the clusters and dipoles and free vortices are. So you can see here that it's identified 2 clusters, a dipole, and some free vortices. So I won't go into the detail of how the algorithm actually works, but it's basically just looking at the distance to nearest neighbor vortices. And the solution that you get out for any vortex configuration is unique to the algorithm. So you always get the same answer.
10 and 9, you can consider them separate or put them in the cluster. How you decide that?
So it's, yeah, you could change the rules of the algorithm if you want, but basically the way we've defined the algorithm, you get these 2 being in a cluster. But of course, yeah, you could change the rules and get a slightly different answer. But I think statistically it will come out basically behaving the same way for these results at least. If that makes sense. So yeah, I suppose the rules are in some sense arbitrary, but this is what we decided. So then what we can do is we can actually set the temperature using Monte Carlo simulations. So we can actually sweep out this whole phase diagram and see how the vortex gas wants to behave at each temperature. So on the left here, I'll show you an image, I'll show you a movie, sorry, of the Monte Carlo simulations that we ran, where we just put in, I think it's 20 or 40 vortices, maybe 50 even, and basically applied this classification algorithm at every temperature. You can see along the bottom, there's a legend for what you're actually going to see here. So at the moment, the beta, the temperature, is deeply in the positive regime, which is somewhere over here. And you'll see we'll sweep through to the negative temperatures. So at the moment, we just have dipoles. If I hit play, we'll see that we start sweeping the temperature up here this way. So you can start to see as beta approaches 0, we're right in the middle of this diagram. And you can see there's a mix of dipoles and clusters and these free vortices. And then as we keep going this way, the vortices start to combine into these clustered states. And so once you hit -1 in these units, they really clump into these 2, almost like multi-quantum vortices.
So can I ask, so
Yep.
Is that sufficient?
Sorry?
Is that sufficient in this?
No, this is equilibrium. This is thermodynamics. This is you put in a temperature and you just walk the vortices around just in a Monte Carlo fashion.
No, I'm trying to, so if I have vortices, then they just go circulate around each other. I don't have dissipation, right?
Yes, and dynamically they will.
Dynamically.
But this is thermodynamics. This isn't.
So yeah, so the number of vortices would always go down.
In dynamics.
Yeah.
Yes.
There's no process of creation vortex.
There can be in principle, but usually in Bose-Einstein condensate systems, yeah. So if you increase the temperature of the gas, you can get vortex anti-vortex pair creation, or you can stir the fluid yourself and create more vortices. But if you just put in like the initial condition that I showed you before, you'll never get pair creation basically.
So this is like a Groszek.
Yes, Groszek, that's the simulation. So this isn't. This is Monte Carlo.
Without noise terms.
No, it's just pure zero temperature. So yeah, this was just Monte Carlo simulations with point and light vortices. So you can make this approximation and write down a Hamiltonian for a point vortex system, as Thomas was talking about before.
And the separation between those vortices in the pumps is larger than the intrinsic size of the vortex?
Once you go, basically, I think it's, I don't remember. I think once you hit -1 here, they're at the size of the vortex.
So then you can think of this as really just a multiple vortex solution.
More or less, I suppose. But if you don't put in like the hardcore radius here, if you let them go towards each other.
Surely, but the radius should get bigger for on ends.
Sorry?
You would think the radius of the core would get bigger for charge in vortex.
Yes, it would. Yeah. So yeah, intuitively, that's basically what's happening. They want to comp into a multi-quantum vortex.
So I didn't understand. What was the Monte Carlo update?
So you can write down a Hamiltonian for the vortex system, which is just dependent on the vortex position.
Did you fix beta?
So yeah, I fixed beta, and then I just calculate the Hamiltonian, and then you have an update step, which is literally just moving a vortex, recalculating the Hamiltonian, and seeing if it's more preferable at this temperature. So you just use the Boltzmann distribution. You just have e to the minus energy over temperature, basically. Okay, so once we've done those Monte Carlo simulations, then as a function of this Monte Carlo temperature that we choose, we plot the population of each of these 3 groups of vortices. So the percentage of clusters in blue, percentage of dipoles in red, and the percentage of free vortices in green here. So don't worry too much about the units here, just the scaling is a bit weird in between the negative and positive temperature cases. And that gives you this weird discontinuity in the gradient here, but that's not particularly important. But what we have here now are monotonic functions of temperature, which is what we wanted to perform thermometry. So the idea here is now that if I'm given some state of 2D quantum turbulence with some configuration of vortices and anti-vortices, I can just calculate the percentage of dipoles, for example, and if I get 60% dipoles, I can trace onto this curve and read off the temperature down here. Likewise for the clusters, that's also monotonic. So any fraction of clusters you give me, I can read off the corresponding temperature. Free vortices we don't worry about because they don't behave monotonically, so they're a bit more complicated.
Quick question, how do those curves depend on the size of the system?
So the size of the system, it's independent. The only thing they depend on in the negative temperature region is the number of vortices you put in. So this curve gets slightly flatter as you increase the number of vortices. So that's...
Can stay here. The numbers depends on the definition of what you define as a dipole, to say distance.
Yes. Yes and no. So it doesn't. It's not like I put in a distance and say anything lower than that distance is a dipole. That distance is kind of calculated from the density of the vortex gas, I suppose. So it's
like the nearest neighborhood thing.
Yeah. So going back to this. Like this dipole wouldn't necessarily not be a dipole if it gets bigger. It's just if this vortex gets closer to this vortex than it is to that vortex, then it wouldn't be a dipole anymore. So it's depending on where the other vortices are.
But for example, if I see 1 plus and 1 minus and 1 plus nearby, then I have to define the distance so that I exclude the next plus. Is that correct? I mean, so that's...
So you don't put the distance in by hand. That's just, it's determined by where the other vortices are in the system. So
I think you throw a dice at that point. Throw a dice.
So in this case,
it's nearest neighbor, whichever one's closest.
Yeah.
Grab those up first.
So in this case, it does look pretty ambiguous because this could always be basically the same length as that, right? So
I guess the question is when you have your dipoles, is there a parameter which says that the separation from the dipoles is parametrically small compared to the separation of particles in the dipole is parametrically small compared to the separation of the dipoles.
Yeah, I think that's
Is there a
the way
parametric
Yeah.
quantity?
So is there a clear-cut separations between
so
for this particular picture,
yep.
Maybe so, but in general.
For example, if you were thinking about particles, there'd be some microphysics scale which would separate, meson and quark and an antiquark and meson. Yeah. Then there's some large distance scale between the mesons which would correspond to that. You control the large distance scale by the overall density,
yep.
But the intrinsic scale of the separation of particles in the dipole is controlled by some microphysics scale.
Okay, right. So yeah, we do put in these well, I guess in the dynamics, it would be the healing length, I suppose, just the size of the vortex core. But in the Monte Carlo simulations that I showed you here, we implement like a hardcore radius because these are point vortices now. This isn't actually a Groszek simulation. So we just enforce this, a condition that the vortices can't get closer than some predefined radius. I don't know if that answers your question.
It's really a question of how far they can get away, how close they can get. What's the typical size scale of separation between your vortex, anti-vortex pair, and your dipoles?
Well, it will get smaller.
Scale.
So as you keep reducing the temperature to this colder regime, the separation gets smaller and smaller, basically until you hit that hardcore radius.
Okay.
So the separation of dipoles depends on this temperature.
But then it depends on the number of vortices that you have in your system.
Yeah, of
right?
course.
If you have more, then it's smaller. If you have fewer, it's larger. So that's the sensitivity that you were mentioning.
There's sort of a minimum radius which sort of forms a threshold. So if they come sort of across this threshold closer, they very quickly annihilate because of the deformation of the density waveform.
Yeah, so in the actual dynamics, so using the Groszek simulations, the dipoles can't get any closer than like the healing length or something like that. And then, otherwise they'll just annihilate in the system. But, so basically, if in the actual dynamics you want to move towards this positive temperature regime, you'll eventually just lose all the vortices because they'll just annihilate once you get to this picture.
What's EBC?
So this is the name for what happens when the vortices, so after they've formed this state, you saw before that they clump down into basically a multi-quantum vortex. And so that was coined by, I think it was Kreinen back in the 70s. He kind of incorrectly called it an Einstein-Bose condensate of vortices rather than a Bose-Einstein condensate. So we just kind of took his terminology and we're calling this an Einstein-Bose condensate once the vortices clump down.
Okay.
And at this end, that's the BKT transition. We have dipoles basically forming or breaking up, which depending on which way you go. So now that we have this thermometer, we've created using Monte Carlo simulations, we can apply it to our dynamical Groszek simulations. So how we do this, we just run some more simulations. So like I showed you before, we have this disk-shaped Bose-Einstein condensate. We put vortices and anti-vortices randomly throughout the system, and we just watch it decay. So again, you see the vortex number goes down. That's this black line here. And you can see these clusters forming over time. And so here are the number of each of these classified fractions is shown here. So the number of clusters in blue, dipoles in red, and free vortices in green. So to use the thermometer, the axis of the thermometer was the population of each of these. So we just divide each of these by the total number. And then you get a graph that looks something like this. Over time in our dynamics, the fraction of clusters is going up and the fraction of dipoles is going down. And then we just put these curves basically into our thermometers at each point in time. So as an example, the last point here, you have something like 60% clusters. So you can read off the temperature, and something like 20% dipoles. So again, you can read off the temperature here. So you get a temperature reading somewhere down here for the final state. And then you just repeat that for every point along this curve. And so we use both the red and blue thermometers here. So you use both of the red and blue dynamical data here, and you get out two temperature readings. And kind of as we intuitively expected, we started near the infinite temperature, this beta equals 0 region, and we moved towards negative temperatures. So this was kind of the first actual quantitative measurement of this vortex temperature, which is a parameter that was put forward by Onsager back in the 1940s. So it's kind of nice that we can actually measure it now. And so this work was published in PRL early last year, if you're interested in taking a look. And if I have time, it's already been half an hour, but the second part of my talk will be on the experiment that was done at Monash. So I had the privilege of working with the experimentalists at Monash University because they basically ended up doing some experiments that more or less confirmed my numerics, and I got to actually help them analyze and understand the data. So that was actually really interesting, despite the fact that I'm not at all an experimental physicist. So before I actually talk about our experiment, I'll talk a bit about the background, kind of the history of experiments in this field and why this experiment was kind of possible now. So the first two experiments on 2D quantum turbulence in boson-Stone condensates were done quite recently, so 2013 and 2014. So this was a group led by Brian Anderson in Arizona, and I think Tyler Neely is going to be here within a few days. And then there's a group in South Korea led by Yongil Shin, and they did a similar experiment in 2014. So here, just like in my simulations, they stir the cloud. I'll get to that in a bit, how that actually happens. And they create lots and lots of vortices and anti-vortices, and then they just watch them decay over time and kind of study the statistics of the vortex behavior. So in these early experiments, there are kind of a couple of limitations, I suppose. So one of the major limitations was that the vortex signs weren't known. There was no known way of actually obtaining the vortex signs from these images. So these are just density images of the cloud. So you don't actually have any phase information from the wave function, and that will tell you the actual circulation of each vortex. So that was one major setback. The other limitation that it turns out is a problem is the trapping potential. So here, and typically, historically, in boson-Stone condensate experiments, the atomic cloud is trapped in a kind of harmonic potential, which makes the density of the cloud vary as a function of the radius. So it's probably clearest in the simulation here, but you can see that the grayscale actually fades away slowly as a function of the radius. So the cloud's very inhomogeneous. And so that turns out to be a problem for looking at this quantum turbulence dynamics. So yes.
Experimentally, how did they create this initial state?
So specifically, I think this one, the one you can do, there are a couple of ways to do it, I suppose. Basically, you just want to perturb the cloud somehow. So I think in this one, they used a laser stirrer, maybe. So you can basically just stir the cloud with a laser, like it was a spoon or something, like you'd stir a normal fluid. And I think that's probably what they did here as well. But you could also just like shake the whole thing, and you'd probably get vortices. You'd probably also put a lot of other energy in that you don't really want. But I think these are probably done with laser stirring. I don't know if anyone can correct me on that.
So those two are different. Quite different. Those two experiments.
I think, I can't remember specifically, but yeah, laser stirring is a pretty common way. So you just, yeah.
So other one is stirring. So many vortices.
Yep.
And for lower case, you have vortex and anti-vortices.
In both cases, you'll have both vortices and anti-vortices. I think the stirring protocol was slightly different, at least between the two, but fairly similar, and you end up with a fairly similar state where you just have.
If you stir like this, you'll create all these.
Yes. Yes. So you don't want to do that.
If you'll go.
You want to get, yeah, exactly.
Like this, you'll create both sides.
Yeah. So that's probably what they did, something like that. So since these experiments, both of these problems have actually been solved. So the first one was vortex sign detection, which was again done quite recently for the first time in quantum turbulence. So the idea here is you have your atomic cloud of atoms, and you shine the laser light from each direction. So that's these arrows here. And each laser kicks the cloud in each direction. So you get some fraction of the cloud being kicked in one direction and some fraction being kicked in the other direction. And then the key point here is that you actually tune the frequencies of these lasers such that they only kick atoms with a particular velocity. So along the bottom here, you can see a case where they've done this, and you might not be able to see, but there are actually two vortices in this system. There's one here and one here. And so what the blue and red images here are these two kick clouds in each direction. You can see that one laser has kicked this blue cloud, and it's created a strong signal near the vortices on either side. And the other one is kicked in the other direction, and it's created a strong signal on the other side. So what happens is you tune these frequencies such that you pick out the strong velocities in the system, and they're the velocities that are going to be close to the vortex core. Because again, the vortex velocity drops off as 1 over r. So you pick out the vortex cores basically by doing this. And then you can tell the sign by looking at basically the ordering of the red and blue here. So if there's blue on the left, that means you have a strong velocity in that direction. parallel to these beams. And if there's red on the right, then you have a strong velocity in that direction, again, parallel to the beams, but in the other direction. So from that information, you can immediately tell that this vortex has to be clockwise, I think it is. And so this one here goes this way. And likewise, you can do the same to the other vortex here. So you see that the red and blue have actually swapped. So this has to be an anti-vortex now. And so when that's applied to a more complex state, you have a lot of vortices and anti-vortices. You can overlay those two red and blue images, and basically you can identify where all the vortices are in this image, and then you put them onto this image, and you try to figure out which ones go blue to red and which ones go red to blue. And by doing that, you can pick up the vortex signs.
Are these expansion images?
Yes, I believe so. So it should be all destructive images. So yeah, this is a fairly robust technique. It seems some of them are a little bit iffy, maybe. They're still fairly clear, especially something like this. It's just kind of noise. But for the most part, it works quite well. So the second problem is the trapping potential. So how you're actually holding the atomic cloud in place. And so the reason we think this is a problem is based on some simulations that I did a few years ago. So basically, I found that if you put this initial state of random vortices and anti-vortices into a trapped boson snake condensate, but you put it in a harmonic trap, so that's the typical one where the density is inhomogeneous, and you put the same state into a uniform disk trap, then what you see is over time that in the disk trap, you see these clusters forming, and in the harmonic trap, you don't really see them forming at all. And so if we want to study this clustering behavior, these numerics suggest that we really want to use a disk trap rather than these typical harmonic traps. So what's happening here is actually there's no real fundamental difference in the vortex dynamics. Clusters are still they still want to form in this case. So they're still going towards that more negative temperature state. But it's just that in the harmonic trap, what's happened is the inhomogeneity has forced the clusters basically to be on top of each other. So you're never really going to see them in an experiment if you use a harmonic trap, because the clusters are overlapping all the time. So to do an experiment, we really want to use a trap that looks more like this than this. So the good news is, again, this was solved quite recently. So one solution is to use what's called a digital micromirror device, or DMD. So this is basically the same technology that's in your common projector. So the idea is you just have some array of pixels. So it might be 200 by 200 sorry, what did I say? You have some array of tiny mirrors. There might be 200 by 200 of these. And then what you can do is you can feed a signal in from the computer, which is this image here, and basically tell each mirror to either be on or off. So here's black is when the mirror is off, and the white is when the mirror is on. And then you can shine light onto that projected image and see what reflection you get out. And that's this central column here. So you can see the light has been reflected from all the white space, I think it is. And it's been reflected from all the black space. It hasn't been reflected from the white space. And so then when you put atoms into these traps, the atoms feel a repulsive force from the light, so they want to sit in the dark regions here. And so this column is what the condensate looks like once you put it into these traps. So as you can see, you can make any kind of shapes you want. As long as you can feed in some binary image from your computer, you can make that in terms of in boson snake condensate. And so the other neat thing here is, again, it's just like a projector. So you can actually just play movies on this as well. And you can get a time varying potential. So you can do whatever you want with your condensate using this technology. So this is really neat. So going back to these early experiments, now we've got a way to measure the vortex sign. And now we also can play with the trapping potential and do whatever we want. So in the kind of next generation of experiments, we were able to look at this clustering behavior. It wasn't really possible before. So this takes me to what was done at Monash University about 1.5 years ago now. And so the goal of this experiment, as you might have guessed already, was to look for these negative temperature clustered states, because that hadn't been done before. And so the experimental configuration looks something like this. I'm not an expert by any means, but I'll try to explain what's going on. The green line, horizontal lines here are called light sheets, and they basically Again, they act as repulsive potentials for the atoms. So you have these two light sheets, and they basically squish the atoms down into a pancake. So that gives you the 2D geometry. And then you have this green line, the vertical one, which is from the DMD. So that gives you whatever 2D trapping you want. And then the red line here corresponds to those Bragg signals, those Bragg beams that I was talking about before, that kick the clouds in each direction and let us measure the vortex signs. So what we get out from this, something like this. So you can see now the density here is quite uniform in this disk rather than being inhomogeneous. And again, we can use these scattered clouds and sum them together just like I showed you before and get out this velocity map, which lets us tell the vortex signs. So everything's in place, except one thing, which is to actually generate the vortices to begin with, is what you were asking before. So the typical way to do this is just to stir the VC, the Bose-Einstein condensate, like it was a regular fluid. So if you stir a classical fluid like a cup of coffee, you'll see you get a vortex and anti-vortex on each side. You get basically the same behavior in a Bose-Einstein condensate. So if I stir this upwards, you can see vortices being shed from each side of the obstacle in much the same way as you see over here. So what we do is we just play a movie like this on the digital micromirror device, which basically acts as a time varying potential. And you can imagine that the vortices that will be shed off this, as it sweeps through the condensate. And so I'll get to it in a bit, but we actually use 5 different grid sizes. So we vary basically the width of these barriers. And as you'll see, the vortices that you get out vary quite significantly depending on which configuration you use.
Can I ask you a question about this?
Of course.
When you have this stir moving up and down, you have a periodic motion. Would it be better to do it this way than again from bottom up, in one direction only? Because
So
it looks like you see going in the opposite direction, kind of cancel the vortices. Into the system. This way you can increase the vortices. So you can do in one direction, stir in one direction.
But it isn't actually circular. So it's the same pattern. It doesn't go.
No, you see, I imagine you have 2 stirs as you go from bottom up, and then they come from top. You see down.
I think I see what you mean.
The stir, you see, create vortices in different directions. Go up and down. But if you go all the time up, you'll create vortices on the left and right in the same direction. That's what I'm saying.
Yes.
But you're just scrambling a little bit.
Yeah, I agree with you there. The reason we chose to do it this way with like the interleaving grids was to try and stop kind of cohesive motion of the whole cloud in one direction. So basically,
I'm not saying that this is bad.
Yeah, sure. Okay.
That one of them might be more effective.
Yeah. So initially we did try it that way. Well, I say we, but I wasn't in the lab. They tried it that way, and they found that basically you kick the whole cloud, you get this whole sloshing motion, which you don't really want. So this kind of cancels that a bit. So that's why we chose to use that instead. So moving on to what we actually found. So these are the kind of density images and velocity field images that we get out. So on the left, you can pretty clearly see where the vortices are. And on the right, again, you see this blue and red velocity map. So the first thing you do is you detect the vortices in this image, and you put their locations onto this image. So like before, what you could do is just look at this by eye and figure out which ones go red to blue, which ones go blue to red, and then figure out the vortex signs that way. But we wanted to automate the process just because we have thousands of these images. It would be really tedious. So the way to do that was, we found, was to generate some numerical versions of these velocity maps. Basically, we just use a point vortex model to approximate the vortex velocity fields, and then discretize it on the same resolution grid as these experimental images. And we also project that velocity field along this direction, again, to directly compare with these experimental images. And then what we do is, once we have this numerical version of the velocity field maps, it looks pretty much the same as this. We compare pixel by pixel to see how accurate that is. And because we don't know the vortex signs here, and we're trying to figure them out. What we do is we just literally throw in every possible configuration of vortex signs that, for this configuration. So we know that there are n vortices, and therefore, and each vortex can have either clockwise or anti-clockwise circulation. So then there are two to the n possible configurations for these vortex signs. So we literally just loop over them all and figure out which one matches the best. So on the x-axis is the configuration number, I suppose, ordered from worst to best. And so there are 2 to the n for n vortices. I can't remember what n this is, probably about 20. And so you literally just create a version of this for each possible configuration and compare pixel by pixel to see whether the reds and the blues match. Sorry. So you can see clearly there's a best configuration up here with the most matching pixels. And in this case, there's actually quite a nice jump between the best and the second best. I don't think that happens in every case, but I think it does happen in most cases. So it's pretty clear which is actually the best configuration. And so once you've done that, you get out some numerical versions of these velocity maps that look like this. And so you can see qualitatively, they look pretty much identical. You can see the red stripes, the blue stripes, red regions here. So it looks like this technique works pretty well. And then once we've done that, we know the vortex signs, and obviously we know the vortex positions from over here. So then we can just use all the same analysis that I was showing you before with the theory. So we use that vortex classification algorithm to identify the dipoles, and the clusters here are shown with lines in between them. And then we can look at how the vortex temperature behaves, basically, to see if we actually have these negative temperature states. So I'll show you some time varying results from this second smallest grid here, because it's kind of the most interesting case. So we start with something like 20 vortices, and over time that decays. So here, every point is averaged over 20 runs. And I should say that each run here is destructive. So basically what you do is you create a state of turbulence, you wait a certain amount of time, then you drop it, you image it, and when you image it, once you drop it, basically you destroy it. So we don't actually have proper dynamics, and it's not the same state evolving over time. It's statistically equivalent states that we're taking various snapshots of over time, and then averaging over 20 or so runs for each time here. And so looking at those classified fractions as a function of time, the clusters, the fraction of clusters is shown in blue and the fraction of dipoles in red. And you can see that the fraction of clusters is going up over time, and the dipoles are kind of going a little bit down. It's not a particularly strong effect, but it seems to be there. And then just like I did with my theory numerics that I showed you before, we can apply these vortex thermometers. So the solid lines here are the same as the thermometers that I showed you earlier. So they're from Monte Carlo simulations. So then what you do is you take each set of 3 points from this graph, and you basically slide it along the x-axis here, left to right, until the 3 points line up nicely with the solid curves here. So you can see these three points line up fairly nicely when you put them at this temperature. And so that temperature is going to be about -0.2 in these units. And so once you do that for every point, you get a temperature curve that looks something like this. So this immediately tells us that yes, we do have negative temperatures. And also we're seeing this behavior where we start somewhere near b = 0 and we move to more strongly negative temperatures. That's kind of interesting. And then we look at a couple of other observables that basically are kind of equivalent. So one is the vortex correlation function. So the details aren't really important, but -1 means you have dipoles and only dipoles, and +1 means you have only clusters. So here you can see we started somewhere slightly negative and gone to somewhere slightly positive. So that agrees with the temperature. And likewise, you can plot the energy per vortex, the energy in the flow field of the vortices, which we can calculate numerically. So that's just an approximation, but again, that shows basically the same behavior.
If you have a single vortex in the system, what would be the energy of the vortex in your diagram?
It depends, so it's whatever units this is calculated.
If you have create one single,
Yep.
in the center,
I don't know
what would be the energy in those units?
I can't remember. So the units here,
It will be bigger than that, smaller than that.
It'll be smaller than that.
It can't be smaller.
Pretty sure, almost certainly. But I can't remember what the, yeah, I couldn't tell you off the top of my head what number you get out in these units. I could calculate it, but I'm fairly sure it would be much smaller.
It will depend logarithmically on the size of the system.
Yes, yes, it does. Okay.
That's
Sorry.
why it's kind of better to be non-reliable.
These ones, yeah. So basically, that's when we have 4 vortices or something left. So it's kind of broken down. So we're not too worried about that, but yeah, it kind of ruins the nice picture that we saw, the increasing temperature. So then we have the same picture for every grid size here, but I won't go through them all. I'll just compare them overall now. So to do that, we took an early time average, which is the average of these 3 points here, the first 3 points, and a late time average, which is the average of the last 3 points. And then we just plot those averages as a function of this grid size. So then you get out a plot like this. So now the x-axis is just this grid, which grid we've used. And then the dark curves here are the early times, and the late are the late times. So you can see that as we make the grid bigger, we go from creating very few clusters and lots of dipoles up to creating mostly clusters and very few dipoles. And likewise, the temperature, we can sweep between about 0.1 in these units up to about negative 0.6 or so. So we clearly have negative temperatures in these states. And similarly, the correlation function and energy per vortex show basically the same trend. So what's also interesting here is that the first 2 points show some evidence that the temperature is actually getting more negative in these two simulations. Sorry, not simulations. These two configurations. And likewise, yeah, the clusters, the percentage of clusters is going up, and the correlation function is becoming more positive, and the energy per vortex is going up. So that's basically in agreement with what I saw in my simulations. By contrast, these other 3 points, either the temperature is constant or it drops a little bit. So yeah, we clearly do have negative temperatures here, and we've been able to show that. So this work is soon to be published in Science, but the manuscript is currently up on the archive. It's a fairly old manuscript now, so it's a bit out of date in some sense, but hopefully it'll be published soon. And I'll just mention that the group at the University of Queensland, led by Tyler Neely, recently got similar results. They did a very similar experiment, and their manuscript is also up in the archive and will also appear alongside ours in Science in the coming weeks or months. So just in summary, most of my PhD was looking at this problem of 2D quantum turbulence and these vortex clusters forming and these negative temperatures, and trying to understand that process. So the theory I showed you was basically explaining how we can now measure this vortex temperature. And in the experiment, we actually observed these negative temperatures and used my theory to prove that we did. So the last thing to do is just say thanks to my collaborators. So Tapio on the right here, I think he'll be here next week. He was my primary supervisor during my PhD. And on the left is one of the Bose-Einstein condensate labs at Monash. So Chris Helmerson is in the middle, and then Sean, to his right, was the main PhD student working in the lab on the project I showed you here. So thank you.
Any additional questions?
I have a couple of questions.
Okay.
When you create lots of vortices, you insert lots of energy into the system, which eventually the system will equilibrate. But during the equilibration, you see the overall, you see, I don't know how, because it's not quite equilibration, you have a temperature. The temperature will go from 0 at the beginning, very close to 0, start increasing. Do you cross the critical temperature at some point? See, I believe you do. But now, if you do, you see then you'll see a classical behavior about that critical temperature, not a quantum behavior. And I don't know how you can distinguish between the two regimes.
Wait, sorry, by the critical temperature you mean of Bose-Einstein?
BC.
Right, okay.
Because you're not going to have vortices about the critical temperature.
So
you don't have a turbulent motion of a classical gas.
Yep.
You don't have quantization, you don't have anything. So the amount of energy you insert into the system at the beginning by stirring, you see, it could be enormous, and
yep.
you can bring the system into that state.
Yes.
Do you or you don't?
No.
So this is one question. The second question is, you simply neglected completely the role of dissipation, you see, in this analysis.
Yep.
How important that is.
Right. Okay. So your first question, we definitely don't get into, don't cross the BC temperature. So this is always condensed.
Because you never discussed it.
Right. Okay. We know that because you don't actually input that much energy by imprinting these vortices. So you increase the condensate fraction. Let's see. So my initial state. Ooh, okay, it's gone. Sorry.
You broke it.
I did break it. So if my initial state looks something like this, by imprinting those vortices, you increase the condensate fraction, sorry, decrease the condensate fraction by maybe 5 or 10% at most. So at the beginning of the simulation, I had 100% condensate fraction. And by imprinting that.
No, but this is a non-equilibrium state.
Sorry, okay, yes, I'll re-explain that.
So
if you let this evolve until all the vortices decay.
But you don't have dissipation, you cannot see that. So you have to calculate the total energy of the system.
Yes, exactly.
But it's conserved.
Huh?
It's conserved.
No, it's conserved, but you calculate that and compare with the energy of the system above the critical temperature.
Okay, no,
is it below or low?
It's definitely below. So here, as I said, so we start with, before you imprint vortices, you have a completely condensed system. By imprinting the vortices, and then if you wait for infinite time, basically, all these vortices will annihilate. You'll just be left with some fluctuating field. That field will have some energy that corresponds to about probably 90% condensate fraction, boson state condensate. About 90% condensate fraction. So
what would be the equivalent temperature? It'll be below the critical temperature or not? This is my question.
Yeah, no, well below. Well below.
Condensate fraction will go to 0.
Yeah. You see, because calculate the condensate fraction. I don't know how to calculate.
So you can use.
Because I would calculate the total energy.
Yeah. So in this sense, it makes sense. So basically, it's the energy and the norm, I guess, that matters. That determines whether you'll end up above or below. So in this case, you definitely will end up below well below the critical temperature. But in principle, yes. If you imprint something crazy, then you can create way more energy that will take you above.
And there could be an interesting regime to explore as well. You see at which point you see the lose quantum turbulence and
yes.
happens in the classical level.
Okay. Yep.
And it will be about the critical temperature.
Yep.
That would be, you don't know that yet.
Yep. And what was your second question, sorry? So dissipation here. So yeah, the total energy of these simulations is, you're talking about the simulations or the experiments or both?
No, you don't have the normal component.
Yes.
The simulation, GP.
Yeah.
With what kind of limitations GP has, depending on the implementation. If you include dissipation, you see GP, or you will think it's slightly different dynamics.
Yes. So we actually literally just.
That
So I just put a paper up in the archive, basically addressing that. So as you increase the temperature of the background fluctuations, you kind of lose this clustering behavior over time. So what we found was that as long as your condensate fraction is above about 80%, you'll get this behavior more or less. But if you have a higher temperature boson state condensate, then the fluctuations basically kill off this clustering behavior altogether, and you just lose the vortices.
So this is an empirical criterion, 80%?
Yeah, so that's just what we measured in our simulations, which is give or take 80%.
I missed what's really driving the clustering behavior.
Right, okay, I didn't actually talk about that, sorry. I tried to shorten my talk, and that's kind of an important thing. So,
I think the question's obvious.
so yeah,
What drives the clustering behavior?
yes. So yeah, so the clustering behavior is happening because the temperature is increasing, or vice versa, whichever way you want to look at it. And so that behavior is driven by annihilations. So just to give you an idea of what an annihilation looks like in these systems. These two vortices come together, and in this case, they collide with another vortex and dissipate into sound waves.
So I assume it's density of the phase.
Sorry, yes. Yeah, density on the left, phase on the right. So you can see the phase singularities around each vortex here. You see them here, and you see that they eventually combine, and then the phase singularities disappear. You lose those vortices. So hopefully this works. So the clustering behavior is, so the increase in temperature is driven by these annihilations. So what happens is that you have some state of vortices like this. You can kind of plot how much energy each vortex contributes to the total energy, which is this x-axis here. So how many vortices contribute how much energy to the total configuration. And as I was talking about, when you put two same-sign vortices together, the energy that they create, I guess, or that they contribute is much higher than when you have two opposite-sign vortices put together. So in this kind of distribution, the clusters are always going to be the most energetic vortices. So they're the most energetic particles here. The dipoles are always the least energetic. So then what happens is that in the dynamics, it kind of self-selects out the dipoles because they're the only ones that can annihilate. So what happens is the lower tail of this this distribution. So for example, those two dipoles there annihilates, and then the mean of that distribution goes up because you lose that lower tail. So you've lost the lowest energy particles from the system. The average energy of the remaining ones goes up, and so when that rethermalizes, the vortices move around a bit. You'll get a distribution with lower total energy, as you've lost some of the integral under this curve, but a higher average energy. And so we've called that evaporative heating. So you lose the lowest energy particles from the system. So that's what drives the evaporative. So that's what drives the temperature. And again, importantly, the energy per vortex. So it's like you're losing energy more slowly than you're losing energy more slowly than you're losing vortices, basically.
When you calculate energy per vortex, is the total energy divided by number of vortices, correct?
Is the total energy in the vortex field.
In the vortex.
So it's just the, 1.5 velocity field around each vortex.
How you remove the forwards from the
Okay, so you split up, again, I think I have something on this, but so the kinetic energy in the system can be split into 3 parts, I think it is. So you can split, you basically split the velocity field of the fluid into the incompressible and compressible parts. So the incompressible part tells you the divergence-free part, and the compressible part tells you the non-divergence-free part, the curl-free part. Yeah. So it's you only calculate the energy in the fluid that's kind of circulating.
Correct, the separation is strictly correct.
Not strictly, but it's a very good approximation.
Oh, sorry?
It's a good approximation.
It's a good approximation. Okay.
Yep.
I have not understood how you include dissipation in your simulation. Could you use?
So there's no.
But if you want to include dissipation,
okay, right.
You have to use the stochastic formulation.
Yeah, you can do that.
Maybe you can couple the GPE.
Sorry.
Equation for the thermal atoms.
Sorry, say that again.
You can use, I guess, the stochastic formulation for the GPE, or maybe another way is to couple the GPE to a sort of kinetic equation for the thermal.
So yeah, that's basically the two common ways to do it.
A source term in the GPE and the kinetic equation accounting for the collision between
that's exactly it.
Thermal atoms and 2 thermal atoms and 1 condensate particle. Am I right?
Yes, more or less. So yeah, there are a few well-known techniques, I guess, to do that.
I think that's Saremba and Nipponic.
Yes, exactly. Okay. And then the other one is called a C-field approach, which is kind of a classical field approach. So it's kind of similar, but not quite the same.
So is the summary of how the clusters form essentially just the dipoles disappear and then you're left with clusters?
So not really, in the sense that it's not like the clusters are there to begin with and you've just lost everything in between. But it's like you start with a random state and then it organizes itself such that you'll get some dipoles out. And yeah, basically it's like if you have 4 vortices, 2 of each sign, if you move the dipoles close together, you can move the clusters close together as well, because it's like the dipole will be giving energy to the clusters, if that makes sense. So you're just redistributing the energy among the vortices such that the remaining ones have more energy. That makes more sense.
So if at any time we have these big clusters, we can always force grain and get a force grain field, force grain vorticity field or something.
I suppose. So vorticity is a bit annoying to deal with because it's 0 everywhere except in the vortex cores. But you can, so I guess I showed you somewhere. You can get out the velocity field. something like this. So you can just sum all the velocity fields together and get kind of an overall flow field. So you get streamlines. Is that the kind of thing you're thinking about?
Kind of in the sense like, let's say in the extreme limit, can I recover some kind of a two-fluid model?
With the two fluids being?
I mean, let's say all your vortices in the superfluid component are in the superfluid component of the two-fluid model, whatever consider here, and then let's say in your particular simulations or experiments, whatever phonons or problems you have, you consider that as a normal fluid.
Oh, okay.
You get an effective two-fluid model.
Yes, you can do that, sure. So these streamlines are basically in the vortex velocity field. So you can obviously look at the velocity field of the phonons as well.
I have one more question. Probably I still missed the part that classify things into dipoles or something.
Yeah.
So now we actually have three numbers, three probabilities. Clusters, the three ones, and then the
yeah. Okay. So the population.
Basically, there are actually two numbers, right? There's a number. We have some total numbers. And so, how do I know that each configuration can be mapped into one particular temperature? Yeah, just this one.
Yep.
So why it should be, because I have two numbers there. So why would it be just one temperature?
So I think the point is that these are just the equilibrium configurations. Yeah. So you can obviously construct some state you want to have any populations you want, basically. But that wouldn't be an equilibrium configuration. So if you,
but then you are doing the dynamics, right? So I think that's exactly my question. So if every single point, how do I know that I can meet off this particular temperature that you define?
Right. Okay. So how do we know that the dynamics are actually in equilibrium?
So is the question, are the dynamics adiabatic or not?
Yeah, basically. My question.
Well, maybe you can put it this way, right? You have a definition for this temperature that you finally report it to be. And I just cannot connect every single picture in the dynamics with that particular temperature that I have, because you still have more choices than just one beta. So I got a little bit stuck there.
Right, okay. I think I see what you're saying. But in principle, if you were just to run the dynamics in the Groszek model, so these simulations here, but somehow take out vortex annihilation, so just allow the vortices to move around for some really long time scale, that will definitely arrive on one of these curves. It will arrive somewhere in this curve. So because, well, the way we've calculated these is actually just an approximation for the disk-shaped trap, but it's very good, I guess. You could, in principle, trace this out using actual Groszek simulations as well, but it would be more difficult. So in that sense, I'm not really concerned that at least eventually you wouldn't get a well-defined temperature. I don't know. Yes.
I mean, going back to this previous picture, you have thermometry. I mean, this is set up where you sort of do a simulation with your simple kind of model, put in the temperature, and then you get sort of three kind of gauge curves, don't you?
Yeah.
And then you try to fit your kind of measure three numbers to these curves. So if they are off, then you should have either a measurement error or be out of equilibrium.
Yeah, exactly. So I think, yeah, you'd be out of equilibrium if you had numbers that, yeah.
Go back to the experimental data where you showed the little picture of the
That's the innovative question.
Somewhere. Sure. This one?
Yeah, so that oval is sort of your proof that you're actually, that this works.
Yeah, exactly. So in principle, yeah, you could have like a fraction down here and a 3-point fraction up there, and then it wouldn't fit anywhere on the curve. So that's when you'd know that you're definitely not in equilibrium.
So from this, you essentially conclude that you're not, so within errors, you are not away from equilibrium.
Yeah. And so we also had some kind of microscopic arguments for why we should be in equilibrium in the dynamics as well. there is also justification.
So you have these kind of decay measured later on as well. Does that fit to moving along these curves then also?
Wait, sorry?
I mean, when you annihilate your vortices, I mean, you had also, I think, studied later on sort of how they annihilate in time. So during that slow annihilation process, do you move along these curves, or can one not say that?
Wait, where? Was that in the experiment?
Stone, isn't it?
Sorry?
That's the John Stone paper, isn't it?
Yes.
You had a second version, and there you had measured these kind of.
So like the rates.
Yes.
Is that it? So like the rate of annihilation versus like the rate that it reconfigures? Yes.
I just remember.
Yes.
I'll have to.
No, that's okay. Yeah. So basically we found that by our argument, the vortices should already be in equilibrium like before this, the first measurement we took even. So it happened somewhere before 0.5 because the vortices move so quickly that they can reach this equilibrium state so quickly. Yep.
Now, talk about 2D. I don't know if you ever considered 3D.
Not myself, but
This type of classification 3D could be a nightmare.
yes, I totally agree.
Maybe
I didn't ever think that.
I've never thought about it. I don't really want to.
No, I don't think it will help because you can have closed vortices. You can have them link. You can have all.
Yeah, exactly. We get very complicated.
The statistics might hold in slices.
Well, yeah, it depends.
That's a vortex anti-vortex
Because you
pair.
can rotate it like this if you change the sign.
Right, you have to do that. Well, okay.
No, you see, that will be totally different. How do you take slices? Which way?
Yeah.
Wondering.
So you have to take all slices.
No, no, because if you have one orientation, then it's scramble everything.
Yeah.
So this is limited to D and so far.
I think so, yeah. Well, yeah, this whole temperature picture is limited to 2D, so I guess in that sense,
It's not at all clear to me that if you took a 3D system, you sliced it in a bunch of ways, and then did statistics on that. Exactly, and then you do statistics on that.
No, but you do statistics, you'll scramble everything, and nothing will be there.
Oh, no.
Yeah.
You'll have to correlate. Well, okay. Question. All right. So let's postpone any other discussions for lunch later today, but thank you very much for the talk. And